The goal of today's lecture is to finish off the proof that the general recursive functions are representable, and the only thing that we have left to do that is the only thing that we have left to do in order to achieve that is finish off the proof from last time, which was erroneous. The first half of the proof that was presented there was perfectly correct, but I begun an incorrect argument towards the second half of the proof, but that proof has now been fixed, which I'm happy to say. And then after this, we're going to prove that the general recursive relations are representable as well. And this will follow as a corollary from the fact that the general recursive functions are representable. And don't worry, I'll remind you what it means for a general recursive relation to be representable once we get to it. Okay, so I'm presenting the second half of the theorem that is written on the board at the moment. So let me draw a red line where the statement of the theorem finishes. So let me just remind you what this says. So suppose that we have a function f, which is going from m copies of the natural numbers to the natural numbers. And let's assume that this is represented by this formula, say, so capital F will denote the representing formula for lowercase f. And then we also have to assume that f is suitable in the appropriate sense that if we have any m minus 1 tuple of natural numbers, that there always exists an extra natural number such that when I evaluate f at that extra natural number plus that sequence in the hypothesis, then this evaluates to 0. We need that in order for this function that I've written down here to even be well-defined. So if lowercase f is such a function, then the theorem is saying that mu f, which is the function that takes n2 up to nm, so an m minus 1 tuple of natural numbers, and maps it to the least such n1, so that f of n1 up to nm is equal to 0. And the claim is that that function is representable, and it's represented by the formula that we have down here. So I'm defining this formula to be g of x2 up to xm comma y, and it is f of y x2 up to xm 0. So the way that we think about this is that f evaluates, y comma x2 comma up to xm. Well, I've said 2, 0. So we think about that as f evaluates to 0 on this input. And then we're also asking that for all w less than y, it's not the case that f evaluates that tuple to 0. So this is saying that the variable that we look for, y, if such a y exists, is this least n1, such that f of n1 up to nm is equal to 0. Okay, so that's the formula that we claim represents this function mu f. And the half of the proof that I had already shown last time was the following. So we just assume that we have these natural numbers n2 up to nm as well as k, such that mu f of n2 up to nm is equal to k. And in such a circumstance, Q can prove that for all y, if y is equal to k underline, then that implies g of n2 underline up to nm underline comma y. So recall, in order for a function to be representable, we need this statement to be provable, but we also need the reverse implication, which I've just drawn in purple there. I'll get rid of that now. And so that other implication is what we have to show today. And I've also written these two statements down here. I'm going to use these as part of my proof. And these are just facts that I derived in the first half of this proof. So you can go and look at the previous lecture or the notes there if you want to remind yourself of how we proved these. But I'm going to use these in the second half of the argument. Okay, I'll jump over to the next board and get started with this. Okay, so we need to show this reverse implication, which I was mentioning. So we need to show that Q can prove for all y f, sorry, not f, g of into nm y implies that y is equal to k bar. And the way that we're going to do this is within the system Q, we're going to arrive at a contradiction and then appeal to contradiction elimination or boss elimination, whatever the rule is called. So essentially, last time I was trying to argue that we have on the level of the meta theory that Q with this hypothesis, as well as the hypothesis that y is less than k bar and y or y is greater than k bar, is contradictory. Now, that's insufficient because that merely shows that Q can't prove such a statement. We need to arrive at a contradiction within the system Q, but that's fine. I'm just going to turn that intuitive idea that I have from the level of the meta theory into a solid proof tree that exists within this system Q. Okay, so I'm appealing to a lemma that was discussed last time, which is the fact that Q can prove the trichotomy axiom. So let me remind us of that. Okay, so remember that we have this, right? So what I'm going to do is use these previous two statements that I wrote at the bottom of the previous board in order to show that we always prove under this assumption inside the system Q that y is not less than, it's not the case that y is less than k bar. Conjunction, it's not the case that k bar is less than y. Combining that with this fact then implies that there is a proof tree that exists which begins with this hypothesis, this as an assumption, and then arrives at the fact that y is equal to k bar, and then one can use implication introduction in order to get a proof of exactly this statement. Okay, so all I need to do is construct these proof trees, but that's pretty easy for us because they're already written out in this world. So let me lead you over to these screenshots over here. Okay, so we're looking at the top board to begin with. So what's happening here is I'm starting with this assumption g of n2 bar up to nm bar y, and I just use conjunction elimination in order to get down to this statement. And once I'm there, sorry, I just moved my character around. Once I'm there, I can use for all elimination with the particular substitution of w for k bar, and we just get this statement. And the point now is that if I was able to prove that k bar is less than y, then I can use implication elimination and derive this statement. But we already saw at the bottom of the first board that I was drawing on that Q is able to prove this statement. So all I've done here is I've let pi be such a proof tree whose conclusion is that statement. And we can see that now we've proven the statement F along with its negation. And so why is this negation elimination? Is that incorrect? Is that negation? Oh, no, that is negation elimination. So the negation that we're referring to is this one. So yeah, we've now used negation elimination in order to introduce this bottom rule, which implies that we have a contradiction, And so then we have negation introduction, which discharges a hypothesis, and the one that we're discharging is this one up here, that k bar was less than y. Okay, so that shows us that under the hypothesis G, with the appropriate variables substituted, that we can prove it's not the case that k bar is less than y. We're nearly complete. We just need to show the same thing, but it's not the case that y is less than k bar. For this, we appeal to the proof that's on the bottom board. Okay, so this is slightly different. Recall on the bottom of the first board that I was writing on that we also have that Q can prove for all w less than k bar implies it's not the case that f blah blah blah. You can just look over to your right and see that. And what I've done is I've let zeta be such a just be any proof whose conclusion is that statement. Because once I have that, I can then just use a very similar style argument to what I used just before. So now I can use for all elimination, but this time choose y to substitute for w instead of k bar. And then we just end up at exactly the same style argument. So now if I was able to prove that y is less than k bar, I would be able to do an implication elimination and derive it's not the case that f, y, n2 up to nm 0. And then just don't forget that we've already shown that we can prove, sorry, we're assuming G to begin with, and we just use a conjunction elimination in order to get the appropriate statement for F. And we've now proven the statement as well as its negation, so therefore we can use negation elimination and derive the bottom rule, from which we can then use a negation introduction rule with this hypothesis discharged. And now we have got the respective proof that it's not the case that y is less than k bar. Okay, and then I'm leaving it suggested that from these you construct a proof tree that, I guess I can write it here, that Q shows G y bar implies y is equal to k bar, which is what we had to show. Okay, so that's the fix for that argument, and that's the end of that lemma. Any questions or comments?
Makes sense to me.
Nice. All right, let me go back over to the second board and I'll keep talking. Okay, I'll just draw a line there. So now we've done all of the hard work in order to prove that general recursive functions are representable. So this is the major theorem. And the proof is a simple induction on the definition of the general recursive function. So the general recursive functions are defined inductively, and originally we defined it using multiple clauses, but we used the beta function lemma argument in order to reduce the inductive clauses that we needed to consider, and then we considered the base cases of that definition along with the inductive clauses. So now we just induct on that structure and appeal to all of the lemmas that we have shown so far. Okay, cool. So that was a lot of hard work in order to get there. And then a simple corollary from this is going to be that the general recursive relations are representable but I know I just paused for comments, but I will just pause again here because this is a substantial point. Did you have any comments to make at this stage, Billy, or is that all clear?
Nothing on my mind at the moment. Could you just remind me what? Actually, yeah. Could you just overview what's the structure that we're doing an induction on? Like, what were the base cases and what were the?
Oh yeah. So the point is that the definition of a general recursive function is you're either the zero function, the successor function, a projection, and then, well, I gave two definitions of general recursive functions, right? So
Right.
one
You're
of
doing
them
induction
was,
on the second one, the one with the
yeah,
beta
I'm doing
function.
induction on the second one, right? Because it avoids one of the inductive cases that we want to
Right.
see.
Could you remind me what? Could you describe the second one? Like, what are the?
Yep, I can do that. Do you mind if I just say it out loud though, rather than writing it down?
Oh yeah, absolutely.
Okay, cool. Okay, so what is the definition that I'm using in this theorem of a general recursive function? Okay, the zero function is general recursive, so is the successor function, so is any projection, so is addition and multiplication, and then also the characteristic function of equality, right? So that's the function. It's the characteristic function of the diagonal, right? So n cross n to n, then n1, n2 maps to 0 if n1 equals n2, n1 otherwise. Okay, so they're the base cases, and then the inductive cases were the composition of general recursive functions is general recursive, and then the minimization of general recursive functions where there always exists a first element that I guess the condition that you say is I don't know what the general name for it is, but I can give you I can write that down. So it's what I wrote down earlier. If f from nm to n is general recursive, and there's this vanishing condition for all n2 up to nm of n m minus 1, there exists n1 in n such that f of n1 up to nm equals 0, then mu f is general recursive. Right, and mu f maps from n to the m minus 1 to n, and it just takes a m minus 1 tuple n2 up to nm, and it maps that to the least n1, such that f of n1 up to nm is equal to 0. Does that make sense?
Yeah, cool.
Okay, nice. And so, yeah, the point is we went through the base cases as their own lemmas, and then we went through the two inductive clauses. So the big difficult parts of the argument were composition of representable functions are representable, and this minimization one is. Okay, so when you have
before that, we went through why you can recover primitive recursion from this beta function, right?
Yes. Yeah, that was the point of the beta function lemma. So that has all gone together in order to get this theorem that the general recursive functions are representable. Make sense?
Cool.
Okay, so that's really good. Now I can tell you how we get that the general recursive relations are representable. So I'll do that on the other board. Okay, so let me remind you what a general recursive relation is. And let me plug in my iPad before this inevitably dies by the end of it. Okay. Oh, where did I write that? A relation is representable it says is representable if there exists a formula R x1 up to xm such that for all n1 up to nm, an element of n to m, if n1 up to nm is an element of R, then Q can prove R of n1 underline up to nm underline. And if I should have put an nm there. And if this is not the case, so if that's not an element of R, then Q can prove it's not the case that R of n1 underline up to nm underline. Okay, cool. And maybe I'll remind you all what it means for a relation to be general recursive as well. So also,
Sorry, just before you do that.
Yep.
This looks more like the first definition we had for representability of a function. We said something like this, and then we strengthened it to a different version of representability.
Yeah.
And yeah, I think the purpose of that was that we couldn't do composition with this kind of definition. And like, of course, it's still true that a composition of relations will also be representable because it's also a relation. But I don't know. I'm curious what you make use of representability of relations for, and if that would have any effect.
What do you mean by what I use representability of relations for? I use representability of relations in the construction of Gödel sentence, right? But is that what you mean?
Yeah, like as in because we ran into an issue where the definition of representability wasn't strong enough for something with representability of functions. So
yeah, that's not going to arise here though. The reason why is because it's because a relation is general recursive if its characteristic function is general recursive, right? And so what we're saying is that a relation is general recursive if its characteristic function satisfies that stronger hypothesis that we ended up introducing, right? And so that strengthening is...
Wait, could you repeat that? Just the last bit?
So a general recursive relation is a relation whose characteristic function satisfies that stronger version of representability that we ended up using, right?
Wait, no. General recursive. The definition of general recursive is completely independent of representability.
Yeah, I'm trying to say that. So maybe I misspoke. Let me try again. A relation is general recursive if its characteristic function is general recursive, right?
Yeah, but you then said that which involves that stronger definition of representability.
Okay, sorry, I don't mean to say it involves it. I mean to say it implies it, as per the theorem that we've just proven.
Oh, okay. Yeah, okay.
Yeah. So therefore, it's not that surprising that this ends up holding, right? This is the weaker version, and I pray to God it's all that I need. But
All right.
it
Well,
will follow.
that was what I was like, just wondering. Is that all you need?
I have absolutely no idea. I guess time will tell. I hope so.
Okay.
I haven't finished the whole part of the argument yet. Um, but this is solid. So let's get this down and then see what we
Yeah.
end up using
Like
later.
I don't think it's a big of a deal because if it wasn't strong enough, we wouldn't be changing a definition. We would just be saying, "Wow, well, notice that a stronger condition holds." Because this is a theorem. This is not like a definition
Yeah,
of.
yeah, that's true.
Oh, I suppose it is a definition, but I don't know. We could just.
Yeah, I think. Yeah. Let me just finish this sentence. No. So what I thought you were saying there is, yeah, this is a definition for sure, but we just might not end up using the fact that a particular relation is representable. You know, we might decide later that there's a new version of representability which is a stronger one than this, and then there might be an extra lemma required in order to push it out to there or something.
Yeah.
But I think this will still be used. Okay, so once we have these two definitions, we can now state the lemma or proposition, I suppose. So prop, the general recursive relations are representable. Okay, and proof. So let's assume that we have a general recursive relation. And let's consider the characteristic function. Which is general recursive, and hence representable. So it's general recursive by definition, it's representable via the previous theorem. And let's put a name down, let's call it R, capital R. Okay, so the condition that we have is the following. So for all y, oh yeah, so now we say, so say n1, oh no, I shouldn't have done it like that. Say n1 up to nn are natural numbers and they're inside this relation. Then I want to tell you what the actual condition on the formula capital R that we have is. So say n1 up to nm is an element of R. Then for all y, so Q can prove for all y, R of n1 underline up to nm underline y, if and only if y is equal to 0, right? So just don't forget that our convention is that if an element is inside a relation, then the characteristic function sends it to 0. Okay, cool. So now there's a clever trick, and the trick is to derive from this a new relation, and that new relation, a new relation, and that relation is going to be the one that represents lowercase r. So I'll move to the first board in order to write that down. Okay, so here comes the clever trick. So now consider R of x1 up to xm of 0, right? Now this kind of makes perfect sense because we know that that Q can prove this thing only if n1 up to nm is an element of our relation. So this is clearly the formula to consider, and we denote this by just r hat of x1 up to xm. And then the claim is that hat represents r, lowercase r, as a relation. Cool. So let's prove that. Let's n1 up to nm be an element of R. Then Q proves, as I already mentioned, for all y R of n1 up to nm y, if and only if y equals 0. And then we can observe a proof tree, which I think is inside this world somewhere. Yeah, this looks like it. Okay. So let's pay attention to the screenshot, the photo, whatever, on the top. And all that we're doing here is deriving capital R of n1 down to nm of 0. That is what we've defined R hat of n1 down to nm to be. So just remember that this is equal to R hat n1 underline up to nm underline, right? And so what this proof tree shows you is that Q can derive R hat of n1 underline up to nm underline, right? That's the first half of the proof complete, because this shows you that if n1 up to nm is an element of lowercase r, then Q can prove this formula. Nice and easy, right? And maybe I'm jumping between the boards a little bit. Yeah, I'm gonna make the second half of the argument, and then I'll go back to the board and summarize. So now we can look at the second screenshot that's presented here. Is this the right thing? Yeah, this is the right thing. So what's happening here is now we're assuming, so it's no longer the case that n1 up to nm is an element of R. Now we're assuming that n1 up to nm is not an element of R. So I'll write that up here. Assume that n1 up to nm is not an element of lowercase r. Okay. If we have that, then by way of the fact that the characteristic function of lowercase r is general recursive and therefore representable, represented by this capital R, we are able to prove this statement inside Q. And so therefore we have some proof of that. And then it's just a matter of getting down to the fact that 0 is equal to 1, which is a contradiction. We just do that using, well, let's go through it. Okay, so we start at the top and we use conjunction elimination in order to just get this single conditional arrow, because then we can use for all elimination, and we pick the particular constant 0 to be substituted in for y. Okay, and now let's assume it was the case that r n1 up to nm comma 0 was so, right? Let's assume this so that we can then arrive at a contradiction and discharge this hypothesis later. Then we can use implication elimination in order to just get this statement that 0 is equal to 1. And that's very easy to contradict. We've done that several times already. But what's happening here is we have inside a one of our axioms of the system Q is that for all x, it's not the case that the successor of x is equal to 0, right? And so we just take that axiom and then substitute and then apply for all elimination, substituting x for 0, and then we get this statement. And that doesn't depend on any hypotheses. We've only used an axiom of the theory there. Cool. And then these are the negations of each other. Don't forget what one underline is. So one underline is the successor of 0. And so therefore we get negation, elimination, we arrive at a contradiction, and then we can discharge the original hypothesis, which is this one up here, in order to show that this is not provable. And then we just remember that R n1 up to nm0 is R hat n1 underline up to nm. Cool. And so now we've shown how to prove that if n1 up to nm is not an element of our relation R, then Q can prove that it's not the case that this formula holds. Okay, and that's a complete proof. I'll write a summary on one of the boards in a second, but are there any questions whilst I'm hovering over the stuff I've just scribbled on? All right. So, yeah. Okay, and that's exactly the definition that I wrote down of a relation being representable. So that's a complete proof.
Thanks.
Okay, so that's it. That's the end of this entire section on Gödel's incompleteness theorem. So proving that general recursive functions are representable and so are general recursive relations. The plan now is to pause on this lecture series. We will return and we will complete the proof of Gödel's first incompleteness theorem. But I think I'll just make a comment. So let's not forget that at a particular point, we used this beta function lemma, right? So this is what I was recalling earlier. We started off with a definition of what the general recursive functions were, and it included an extra inductive hypothesis to what we in fact ended up using. We used the beta function lemma in order to reduce the inductive clauses so that we then had an easier set of things to work with whilst we tried to argue that the general recursive functions are representable. And then we did and then we tackled that via a series of lemmas. So I argue that there's a dissatisfaction that's kind of part of this, and the dissatisfying part is now if I give you a general recursive function as per the original definition that I gave you, and then I gave you the sequence of general recursive functions that lead up to the definition of that one, you can't easily convert that sequence of general recursive functions into the representing relation, the representing formula, sorry, just by reading off that construction and then looking at the representing formulas that I wrote down in all of the individual lemmas, right? You can't do that. The reason why is because I might use primitive recursion as a step inside my definition of a general recursive function, and then I have to appeal to this sub-process involving the beta lemma, and it's just not clear. So in essence, my argument is that the implied algorithm of constructing a representing formula from a general recursive function is completely obfuscated by this argument. And the way that one would make that transparent is by somehow eliminating the necessity of the beta function lemma that this argument currently holds. So I would like to do that. I would like to find a way to prove this result that doesn't appeal to the beta function lemma. I just want to say, here is the definition of a general recursive function, and here is the associated representing formula built off the inductive clauses, so that you can then extract from that proof an algorithm for constructing the representing formula from a general recursive function. The reason why I want that is because it's not the case that the general recursive functions are indeed needed inside the proof of Gödel's first incompleteness theorem. All that you need is Gödel's sentence, right? And Gödel's sentence at the end of the day is a formula inside this particular system of arithmetic, right? And so as long as I can construct that, I'm fine. I don't ever need to talk about general recursive functions. The general recursive functions is just an easy way to describe Gödel's sentence that I end up using. But the reason why it's easy is because I have access to primitive recursion. So if I was able to do that on the level of the actual formulas themselves, then I could cut off an entire big and difficult irrelevancy to this argument. And indeed, I want to do that. There's only one step involved in doing that. The only thing that you have to do is come up with the representing formula of a function defined via primitive recursion on two representing formulas, two representable functions. So
yeah, I was thinking about that earlier, and I think the use of the beta function lemma is like, I don't think there's too much extra stuff going on than the content of what you would do if you wanted to represent the if you wanted to represent primitive recursion, because essentially it's just doing the task of it encodes like the arguments as a number or something in order to I forget exactly how to describe it, but like my impression is that this is simply like the construction that you're talking about, but it's just like separated into two distinct logical components, where you just go through the beta function lemma, and the beta function lemma is just like a simple setting in order to do that special encoding stuff.
Yeah, I actually think there might be a little bit more to it than that. So don't forget that at a certain point, I had to encode two integers in a single integer in order to prove the existence of a beta function lemma. And the way that I did that was I used an injective function from n cross n into n, right? And that thing was defined by some standard polynomial, which is a standard such bijection. But you're encoding a sequence of integers in a pair of integers that then get combined via that polynomial. So I'm not entirely sure it's really that simple. And at the very least, I would say that it's not direct. So I agree with you that that's the first way in order to attempt to do what I'm suggesting. And I tried to do that, and I came to the same conclusion as you. I was like, yeah, okay, so this kind of works. So maybe you could think about it as, oh yeah, there's a sub-process here where I just do the sequence of the defining definition of a function defined by primitive recursion, and then I just write out all of the details of the beta function lemma, the proof of that, and then you've kind of done what I want. But I'm still not convinced that's the most direct and clear, transparent way in order to do it. I think I know what the actually no, I don't think I know it. But I think that it should be reasonable to just write down the representing formula for primitively recursively defined functions. And even if the proof that that does represent the function is brutal, even if that proof appeals to the beta function lemma or something, that's fine. But I'm not convinced that you can just go into the proof of the beta function lemma and extract a formula from that, which is like in any way cohesive or simple. Like it's gonna have the evaluation of the polynomial as part of it, you know.
Yeah, it wouldn't be simple. I do think the encoding multiple numbers or a sequence of numbers as a single number in such a way that you can decode it. I think that's like kind of essential. It's essentially the only tool that arithmetic has to achieve the general recursive functions. And also with that, like you made a comment about that, like you don't need any of this general recursive stuff if you have the sentence.
Mm-hmm.
And I think that like I don't think that diminishes the importance of like introducing and talking about the general recursive functions or their relevance, because yeah, the sentence is like will always be there. The sentence will be there regardless of the axioms of the proof system of arithmetic. Like you can always construct the same sentence. So what's the key part is like what makes it the sentence, or like what makes it a Gödel sentence, and that is specifically about like the expressibility of Q in describing arithmetic, and the 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 things that it can prove about arithmetic are exactly the content of like why you're able to represent the general recursive functions. So like I don't know, maybe you can sidestep the general recursive functions, but in order for the Gödel sentence to be the Gödel sentence, there's some path that starts with the properties of multiplication and addition and what Q can prove about them that needs to enable that.
Yeah, but that's just the statement that if the Gödel sentence is provable, then there is some integer m that represents in some way that proof, right? And then you can feed that integer into a Gödel sentence and get a paradox. So that's a property of Gödel sentence. I wouldn't say that's a property of general recursive functions.
Right. I don't think I said that. I just meant that.
But that's the only property that the Gödel sentence needs to satisfy. As soon as you've got that property, you can get a paradox. So the point is either it and its negation is provable or not.
But the reason that property holds is like because of arithmetic. I think that was more the point I wanted to make. But on its relation to general recursive functions, not only are the general recursive functions representable, but actually we haven't even mentioned this, but the only representable things in Q are general recursive functions. There's nothing else. It's so like this is a like the functions that you can represent in Q. That's another characterization of computability. So like the properties and expressibility of arithmetic and like the properties of general recursive functions, the like which one you use to justify the Gödel sentence. Like I imagine you could use either one, and I don't know, like it seems to me that like evidence for arithmetic being relevant is also evidence for general recursive functions being relevant.
Oh,
yeah.
I see what you're saying. Yeah, okay. I'm not sure why arithmetic is really so relevant either. I mean, like, obviously, I understand why it's relevant, but Okay, what am I trying to say?
Like explicitly, you can rub out some of the axioms, and you can extend it a little bit and make a complete system. Or maybe
Yeah.
you don't need to extend it. So like, it's the properties of arithmetic play a role here because that's the tools you have lying around to cause incompleteness. Like incompleteness could certainly arise in like many other proof systems about other theories. So I don't know. This is probably not like a universal truth, but I don't know. Arithmetic just has is just a canonical is just uh, a typical representative of like, oh, here's a simple thing that you'd want to do with a proof system, and here this is why it's sufficient to achieve incompleteness because arithmetic is exactly this expressible. Yeah.
Yeah, I'm just thinking.
Okay. Will, do you want to persist?
Do I want to try one more time to say this sentence?
Yeah, go for it.
Okay. So what I want to do is translate all of the inductive clauses of the general recursive function and the definition of it into the formulas that we use in order to prove that the general recursive functions are representable. So what I want is a bunch of lemmas that are of the form if this collection of formulas are provable inside Q, then this other formula is provable inside Q, right? So what I'm doing is the proof that the general recursive functions are representable, but I never mention general recursive functions. I just tell you a way to construct provable statements out of other provable statements, right? Because then what I can do is I can just say, let me construct a mega sentence for you just by using these lemmas. I just build up a mega sentence, and that mega sentence is Gödel's sentence, right? And then I also prove that that sentence has got a property, and the property is that there exists some integer m that encodes the proof of this statement in some way. And then I just take that integer and I feed it into Gödel's sentence and arrive at the paradox. What I like about that is that we never leave the realm of logic and language. It's kind of like forget computability and everything else that came after those realizations. It's just here's a fact about the system. If I can prove these statements, I can prove these other statements. From that, I can construct Gödel sentence, which has this property, which makes it paradoxical, the fact that it exists. That's so simple, right? And that's all that I want to say. Appealing to general recursive functions brings in like new intuition of computability theory, etc., which is definitely important and has its place, but I just don't think it's necessary for understanding this argument.
Right, but the only problem would be like it would just be like this massively obscure argument that has like it's hard to see the content of it. Like,
I don't think it would be like that. I don't think it would really be like that. It would just be here.
but how would you describe these formulas that you're making? Like, what the hell is going on with them? Why are they? They're just
You can think of them in the way that you think of it's no more opaque than the definition of a general recursive function. Like there's no reason why I can't say, okay, think about this lemma as the composition of provable functions is provable, and the formulas will respect that. You'll look at it and you'll be like, oh yeah, I'm basically just nesting them in. All this is saying is that there is some notion of composition of provable formulas, right? That'll be for the composition clause. And then for primitive recursion, same thing. I just think about it as primitive recursion. Like it's literally no more opaque than the definition of general recursive functions already is.
Wait, then I'm not sure what you're taking out if you're still talking about composition and primitive recursion and all this stuff.
I'm taking out computability theory aspect, right? Like to think of the general recursive functions as the computable functions is certainly not necessary for.
Wait, but like we haven't really made use of like any strict.
No, we haven't made use of that. But what we have made use of is we are using the general recursive functions in order to build a formula, and it's the formula that we're interested in, right? So the general recursive functions are simply a neat way of constructing this big sentence, which is Gödel's sentence, right? And the only benefit that the general recursive functions have over just sticking to the formulas is the fact that you can use primitive recursion, right? You can't do that in the land of formulas because you have to appeal to the beta function lemma, which completely obfuscates that. But say we had a reasonable formula that represents primitive recursion, then there would be no benefit to using general recursive functions. It would just be this new arbitrary definition, you know?
I still don't get what you mean, like no benefit of using general recursive functions, because you just like described like achieving the set of general recursive functions by representing primitive recursion.
Yeah. But I'm drawing a distinction between representable functions and general recursive functions. So I understand that there's a theorem that these things are equivalent. One's one if and only if it's the other, right? But the point is a representable function, unlike a general recursive function, has a formula associated to it, right? And so we can argue the entire thing just using those formulas. And the benefit of that is that you never leave the world of logic and language. I'm just saying use these formulas to construct these extra formulas and you go straight to Gödel's sentence. If I introduce a new set of functions from the natural numbers to the natural numbers, like it's just not necessary. You don't need that as part of the argument. Because it's not the function that we care about, it's the representing formula that you care about.
Right. I'm but you would still have I'm kind of doubtful that like there is a like you seem to be hypothesizing a sort of simple primitive recursion formula or something. Is that correct?
Yeah, I am. Even if the proof that it represents what we want it to represent is very difficult, I think the actual formula itself need not actually be that hard.
I'm doubtful that you can do that. I think you would need to encode the computation as you go, sort of thing. That like it's done in the beta function lemma. And if there was such a so that's just my like hypothesis there.
Yeah, I don't know if you necessarily need the beta function lemma. Maybe you don't need the Chinese remainder theorem, you know? I mean, this is just one way of doing it, and certainly you could derive a formula from that, and yes, it would be a nightmare. But I don't see any reason to, like, believe that this is utterly unavoidable. I just don't think that might be true. Yeah.
I think like there's like sort of two pieces of like say an incompleteness proof with this technique. Like the second half being here's a formula and I know that it's I know that it has these properties that like the Gödel sentence has. I forget what they are, but and then there's the part where you say, all right, this particular theory that I'm looking at, like Robinson's arithmetic, has the ability to like has that sentence that you constructed from like the language of this theory, it has those provability properties. And in the specific case of Robinson's arithmetic, you might use you tell a particular story about why it's the case in this setting. I don't think that's to say that like any of that is like any of that like the properties of arithmetic or general recursive functions like told in that specific way is like an essential component of incompleteness. Like it's just sort of the Q is the setting that where this is taking place in, and so this is a suitable argument for Q. And so like yeah, so the point I'm making is that you just need to like tell some story like about Q that like fills in that argument. I think when you talk about like I think the missing details are like in constructing the Gödel sentence. I think like making use of general recursive functions has some utility in like describing how to do the encoding. And maybe doing that directly with formulas or something would be like even more obfuscated.
Yeah, that's my question though. That's like exactly the question. So the general recursive functions are certainly used here in order to give a convenient way in order to describe Gödel's sentence. But like, is that necessary? Can we just work with the representing functions that we use the general recursive functions in order to describe, you know? I think it could go either way. I don't know the answer to that.
The reason why I'm doubtful that you can just have a simple primitive recursion formula, even if it's at the cost of it being hard to prove it's the right one or something, is I think the sort of idea of it that you're going for is that it involves some kind of formula which describes like an n-fold composition or something, where n is like an actual like argument to the formula, like it's one of the like free variables or something. My like the accumulation of all my wisdom tells me that like that's essentially not achievable in first order logic in Q.
Yeah, I completely agree with that. I have the same feeling, but I don't really mind encoding a sequence as an integer. Like, that's not that difficult, because you could still break it down. You could still just be like, if you have a sequence of formulas, here's the formula that, like, you know, here's the formula that is provable if and only if all of the other ones are provable or something. And so it just represents a sequence of provable formulas. And then once you've got that thing, then you can use that in order to come up with a formula that represents primitive recursion. That's like the obvious place to start. I wonder if it would be that.
Wait, could you repeat that? I didn't really follow.
Well, so yeah, with coming up with a representing formula for a primitively recursively defined function, you could
Wait, are you
break
talking about like doing it in a way that you can like drop in a previously like take some other formula, you can drop it in place, and here's the well I guess you need two for primitive recursion. Take two formulas, drop them in place in this schematic for a larger formula, and then that's the primitive recursion for it? Or are you talking about like arguing in each case. I don't know, because you still want a construction. So like, I was about to say that like in particular, I don't know, it's true that the primitive recursion is like representable, but that doesn't give you any like that there's no construction there. You would like unless you did it, I doubt it would. You could do it on the like recursively on the structure of the argument formulas. I doubt that would be fruitful, but yeah, you like I don't know. It seems like in order for this to be constructive, you need like to do it in a schematic way where you drop in formulas in particular places, and that involves having to solve this primitive recursion problem in general. And yeah, I don't think you can do that without some kind of like encoding of like sequences of numbers into a single number.
Yeah, but that's fine. I'm not so offended by encoding a sequence. It's not the beta function. It's not the core logic and philosophy behind the beta function lemma that I want to avoid necessarily.
Actually, let me ask you about let me point out something. It seems that you have an implicit thesis that there should be some content to that the content of the incompleteness theorem is entirely logical and can be like understood independent of computation, and that like computation is merely a means to an end. And I'm not saying like you're obviously wrong or like on that or anything. You could be correct, but I just want to point out that like idea. Do you have any strong feelings about why that should be the case?
Oh, because that is the case, just not necessarily neatly. Like you can just work with all of the underlying representing formulas of all of your general recursive functions. It's just that when you do the primitive recursive one, like that formula is horrendous, but it definitely exists. The beta function lemma is completely
Yeah, like I understand that it exists, but I I mean like if we want to understand the content of the incompleteness theorem, like why it happens in some essential way is the like heart and truth of that something purely logical that is like because it seems like you want to like bat away the computational understanding of things here. And
first of all, is it really computational? I mean, general recursive functions capture the class of computable functions, but it's not as if the actual computational process here is what we're discussing. That would be the first thing I would say. And secondly, I think I also have an objection to involving general recursive functions, because what do you think a function is, right? I mean, the nature of the functions here has to be understood either meta-mathematically, in which case, I don't know what the hell you're supposed to think about a function when you're not looking at it. It's not like it sits on the page in its entirety. It's an infinite tuple, set of tuples. Or you pick some foundation in which you can express what the function is, but then that's a little bit against the spirit of what the theorem is trying to achieve somehow. I think I agree that you could say to yourself, well, actually a function is a set of pairs which satisfy some formula, and I'll just work with the formula. And isn't that what Will is proposing to do? It does seem actually to be well, how do you think about the nature of these functions when you're sort of not looking at them? They're not things on the page. They're what? What are these functions in terms of? If I really ask you to specify them, how would you do it?
Yeah, I have no clue.
I think I do believe that you can strip away the essence of what has been discovered when we do Gödel's first incompleteness theorem of all of the computational content and the general recursive functions, etc. Like, I would just say that. So where does the computational content arise? If we just worked purely with the representing formulas the entire way, then the point is that we are constructing explicit proof trees, right? So we're saying that every time that we have a statement that is provable, there is some finite constructive proof tree that proves it that you can write down, right? And that's the computational part of it. So the only way that you can end up with complete, consistent theorems of arithmetic is if you were in some way not able to do that algorithmically. You would have to have a non-computable step inside there, right? So that's where the computational content lies. Now let me absolve the proof of it. You're able to absolve it by the fact that I defined Gödel's sentence inductively in that way, right? So I said, if I construct formulas via this process, then I can construct a sentence whose existence is paradoxical, right? That is a logical statement. That means that this process that we have invented of writing down the axioms, writing down the deduction rules, and then constructing proofs from that is now put into question because you have this inherent incompleteness. So I'm forcing you to say, what do you think about proof systems? What do you think about the fact that we end up with either inconsistent or incompleteness when we insist on this is what a proof is, in some sense? I think that's a philosophical, linguistic, logical question, and it comes out of this result. And that seems more natural than introducing computability theory. I think that's my thesis.
Okay, I want to revise my branding about saying computational content a bunch of times, and you made a fair point about it's more computability than like the process, and I think I would rather like restate everything I've stated, but instead of saying like computation, I mean like decidability and computability. And like the reason why I sort of think they belong together is because of the sort of I don't know, there's like, to me there is a like there's a strong relationship between decidability and incompleteness. I guess like that's something that's my impression of things. And so yeah, like I'm backpedaling on the like computational content angle of it, but I still do think there is some essential like thing about viewing completeness as like a like understanding completeness by understanding decidability.
I think we might have to wrap up there, folks, if you want to have a final comment, Will, but I'll need to switch the recording over to Euclid in 1 minute.
Yeah. No, that's good. That's a good place to end the discussion. All right.
Excellent.
Thank you.
Well, thanks very much, Will. Thanks, Billy, for this excellent series of talks, and we'll resume with the rest of the proof of Gödel's incompleteness theorem at some point in a few weeks, months, whenever.
Yep, sounds good.
But this,
Right,
this was great.
Thanks.
Yeah.
Yeah.